Okay, greetings everyone. This is Dr. Ghulam Mustafa Abdo. I'm a postdoctoral fellow at the Artificial Intelligence and Robotics Laboratory in Department of Electrical and Computer Engineering at Aarhus University, Denmark. The topic of our paper is a modular framework for advanced UAV control using Pixhawk Raspberry Pi integration. Moving further, we have common uh, kind of contents. We'll start our presentation by discussing some background. Then we will go for state of the art approaches. What was the problem actually that we are looking for? And then we propose the solution for that problem. We discuss a couple of results and discuss them, of course. And lastly, we just conclude our work. It will also follow some future recommendations and directions, and then we acknowledge a few parties which were involved in this research, followed by the references. So, coming over the background of our research topic is that everyone knows that if they are going to make or design or develop a prototype drone, and the drone is like really into the fashion nowadays. They are utilized for different purposes, environmental monitoring, infrastructure inspection. But then the key goal is to how to control a system which is flying into the sky and maneuvering from one point to another. Most commonly, people are utilizing PID, proportional, integral, and derivative control. But then now, in the era where we are living, actually, we have developed so many advanced controllers like fraction order PID, slide mode control, and model predictive control. And then people are also working on artificial intelligence based control algorithms. So to deploy those control algorithms on Pixhawk, which is a common flight controller, or Raspberry Pi, it's quite difficult nowadays. So what people do, people do propose that control algorithm, but then when it comes to program it on conventional controller, either Pixhawk or Raspberry Pi, which are two main controllers for our paper, our main focus is on those two common controllers which are utilized for the drone prototyping and for drone control, or specifically flight control, if I say. So they have some limitations, like we cannot program these high level control algorithms, for example, fraction order PID, slide mode control, or model predictive control. So this is one of the major issue that people who are working in these high level control algorithms, they are unable to deploy it on Pixhawk. If we see Pixhawk for attitude control, it needs faster frequency rates like around 250 hertz, if I'm not mistaken. And then for position control, it requires 50 hertz frequency. So for attitude control, if you want to move your maneuver drone aggressively, then these control algorithms, which are high level control algorithm, they need a kind of a high computational processing. So you have to move from Pixhawk and Raspberry Pi to Jetson Nano, or maybe much more expensive, processor. So that is the issue, and that is the background of our topic. So if we focus on Pixhawk has limited computational, like we cannot program FOPID or slide mode control or even model predictive control. And its architecture by default is optimized only for low level controls. And wherever it requires higher storage, just like in artificial intelligence based control algorithms, it's not a suitable option. So people are also trying to explore the potential of Raspberry Pi control algorithm. To the best of our knowledge is concerned, Raspberry Pi is also a real-time operating system, but then it is very critical to use it for UAV operations. Mainly, people are using it for computer vision-based control, and because of its lake hardware redundancy, it might cause a lot of latencies and unstable control in dynamic flight operations. So what is the problem? Problem is that right now the controllers, which are cheaper, we are unable to program them with high level control algorithm. That is the problem, the statement of our today's research topic. So what we come up with a methodology where we integrate Pixhawk and Raspberry Pi. We Rather than integration, we can say that we are latching Pixhawk with Raspberry Pi, and through this latching, which means that now we are connecting some of the control pins with our Raspberry Pi. We have RPI pin 0, any model we can use for this one. And then we have some power RPI from +5 voltages, and then we have USB. So we connect some pins over here to our ArduPilot or Pixhawk controller scheme, you can see. And the detailed description is mentioned in our research paper as well. So resulting it in a kind of a framework where Pixhawk will give all the data to Raspberry Pi. And in Raspberry Pi, we actually program FOPID, SMC, or MPC, whatever things we need. So what we will do, we will program it on ROS, and then we convert the control inputs and we give it to our Pixhawk. Pixhawk then trigger Raspberry Pi, and then it will, trigger the motors of our quad router, and it will perform the maneuvering. An additional advantage of using Raspberry Pi is that we can connect GPS directly with Raspberry Pi and camera as well. So it comes with computer vision support as well. So now this research topic is in its early phase, and still we are pursuing the research. So you can see that we have performed a kind of software in loop simulations where we can execute a trajectory in RViz under offboard control using Raspberry Pi and Pixhawk on this left side. And on the right side, you can see that we have performed by giving the control inputs like the position control to Gazebo simulation and telemetry output confirming successful offboard control. And we monitor the position of UAV, and it actually synchronizes with our MAVLink synchronization as well. So moving further, you can see this video, which we have done a software in loop presentation for our topic. You can see that we have here our terminal where we are integrating the inputs, and we are recalling the the simulation, and you can see that it access the Q ground controller station, which is quite famous, and it is interfaced with Pixel. And the main idea of this experiment is to demonstrate an integrated system that is reliable for real-time communication and control feedback. The consistent positional updates and stable transitions between flight modes. And then in addition to that, you can, program high-level control algorithms by integrating Pixhawk with Raspberry Pi, such as model predictive control, slide mode control, or fractional order PID control. So you can see right now that, yeah, so this is a kind of a simulation that actually triggers once you run the code and the flight. This entire demonstration is embedded in the form of link in our paper as well. So if someone is reading the paper, he can access this video, and within the video and the caption, we have provided the code as well, and the entire you know process how to do it. So you can see that all the windows we are opening here, and then let me just put it forward. You can see that inputs have been given over here, and you can see that now the drone is taking off. And yeah, later we will give another inputs. Let's say we give updated the inputs now. Okay. So yeah, see, now we are actually maneuvering the drone in different direction. So yeah, so this kind of trajectory, I'm just escaping because just to show you that, this kind of trajectory we have generated. So this is a kind of a topic which is much needed because our high level control algorithms, for which many researchers around the globe, they are working fundamentally to prove the simulated results, but then when it comes to hardware validation, they don't find any cheaper solution for it. So summarizing everything right now is that our proposed solution is modular and a scalable architecture that actually comes with provision that you can program any control algorithm, and then it provides you dual kind of opportunity, like you if you want to control the drone, and if you want to integrate telemetry, and then you want to integrate computer vision algorithms, then both can be executable. This entire paper, like research paper, comes with a study in software integrated real-time environment where we have integrated ROS2 with Gazebo simulations, and it improves the robust performance of provided solution. Our main future work is now to just deploy the same algorithm on the hardware and fly it for a couple of flight operations we perform. So that is something that we want to check the latency and energy, and then later we optimize it. That is our future direction actually. Now, yeah, I always say that we and our team, we never walk alone. In this entire project, we are very thankful to Artificial Intelligence and Robotics Laboratory. We call it Air Lab, a Department of Electrical and Computer Engineering at Aarhus University, Denmark. And then, yeah, these are references. I really wanted to come in person to this conference, but unfortunately, I had some prior engagements, so couldn't come. So let's just stay in touch. My name is Ghulam Mustafa. I'm a postdoc researcher, and this is my email. So if you have any query regarding this, you can write to me. And yeah, we will. I'll be happy to get connected, and we can collaborate on any aerial robotics topic. So yeah, thank you so much, and I hope you will enjoy the rest of the presentations after me. Thank you.